So let's do another example of a complete hypothesis test. Here, a new cholesterol drug is being investigated in a clinical trial. The researcher hopes to establish that the drug raises HDL, the good cholesterol, above 50. So that's going to be our mu0, 50 is what we're testing against. There are 75 subjects. That will be our sample size n. In the experimental group, and their mean HDL after 6 weeks of treatment is 51.3. So that's our sample mean, X bar, 51.3. Population standard deviation here is 15.4. So sigma is 15.4. Perform a hypothesis test at alpha is 0.05 to determine if the drug is effective. So effective means that it raises above 50. So our alpha is 0.05, and then what about alpha is 0.01? So first alpha 0.05, and then we'll come back and look at 0.01. So verify requirements. The sample is a simple random sample. So, they have not specifically said that the 75 were randomly chosen, but this is a clinical trial, so we will assume that they've used good experimental design here. So we will assume that. Sample size is large, greater than or equal 30. Yes, 75 is greater than or equal 30. Null and alternative. So the alternative is what you're trying to show, that it raises HDL above 50. So that would be mean greater than 50. And then the null would be no effect, mean equals 50. Or less than equal would be fine. Select your level of significance alpha. So for us, 0.05 to start. And then let me go ahead and grab my values here and bring them down. So sketch our rejection region. So alpha here is 0.05. This is an upper tail test, so 0.05 upper tail 1.645. So rejection region is going to be on the right. And marked off by 1.645. So that cutoff for the rejection region is called the critical value, so the Z alpha value. So that's actually our Z 0.05. Next, we compute our test statistic. Here's the formula for test statistic. So our sample mean was the 51.3 minus 50 is what we're testing against. Standard deviation was 15.4. And dividing by square root 75. So let's go ahead and enter that into the calculator. So the 51.3 minus 50, that's just 1.3. So that we can do in our head. And then we're going to divide by, let's put some parentheses in there, 15.4 divide by square root 75. Close up our parentheses. So 0.73. And that is going to be to the left of the 1.645. So right in here is our test statistic. Z test is 0.73. And it is not in the rejection region. So step 5, does it fall in rejection region? If so, reject the null. Well, our z-test here, which is 0.73, is less than the 1.645. More extreme would be greater than. So do not reject H0. And then state and interpret the conclusion. So we would say that there is not sufficient evidence to conclude that the mean is greater than 50. So remember, your interpretation always refers to the alternative hypothesis. So in other words, this is saying the drug doesn't work. Now, what if we had used alpha is 0.01? Well, then our cutoff would have been 2.33. So that would be out here. So that's 2.33. And that was for alpha is 0.01. And we still do not reject. So now if our test statistic ended up in between here, it was bigger than 1.645, but less than 2.33, then we would reject at the 0.05 level, but we would not reject at the 0.01. In this case, it's to the left of both, so we do not reject at either level. And then to wrap things up here, we'll look at the TI commands to perform this test. So we want to go to the stat menu and then to tests, and we want to do a z-test, which is that first one. We're going to input summary data, so highlight data. Our mu0 is 50. Our sigma was 15.4. It's our population standard deviation. I'm sorry. We want to highlight stats, summary stats. So go back up to the top. We're not using the actual data. We're using stats. So 50, 15.4, our X bar was 51.3. And then N was 75. And then we have to tell it that we're doing a upper tail test greater than mu0. And then we can come down and you can do calculate or draw. I'll go ahead and do calculate. So there's our z test of 0.73. It also lists the mean, sample size, the alternative hypothesis, and then this p equals, the p-value. That we will look at in the next section. So we will just ignore that for the immediate time. So this is confirming what we did by hand.